Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 says that the sulfate ion SO4 2- can be drawn in many ways. If you minimize the formal charge on the sulfur, how many sulfur-oxygen double bonds should you draw in the structure? Okay, so let's start off by drawing a Lewis structure of the sulfate ion. And when we write Lewis structures, we first need to find out the total number of valence electrons for this ion. Sulfur contains 6 electrons, and oxygen also has 6, but since there are 4 oxygen atoms, we multiply this by 4. And also the overall charge of this ion is -2, so we need to add an additional 2 electrons to this count. Okay, so in total we have 32 valence electrons. So now let's draw sulfur as our central atom. And then I'm just going to draw 4 single bonds to the oxygens. Okay, so notice how none of these oxygens have a full octet yet. So I'm just going to draw 2 double bonds, 2 of them, and fill in the lone pairs. So I know that single bonded oxygens will contain a negative charge, and I know that the double bonded oxygens will be neutral. So another way I can double check that is by calculating the formal charge. So for the formal charge of an ion, it's equal to the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. Okay, so now that we know this equation, let's check out the formal charge of a single bonded oxygen. Oxygen has 6 valence electrons, and a single bonded oxygen contains 6 non-bonding electrons. And there's only 1 bond to the oxygen, and each bond contains 2 bonding electrons. So we'd write in 2 divided by 2, and that's how we get -1. So I can draw charges of -1 beside my single bonded oxygens. Okay, so let's double check the formal charge of a double bonded oxygen. Again, there are 6 valence electrons in oxygen, and then double bonded oxygens have 4 non-bonding electrons, and they have 2 bonds, so it's 4 divided by 2, and they are neutral. So now let's check out the formal charge of the sulfur. sulfur has 6 valence electrons, and this central sulfur atom doesn't have any lone pairs. So we subtract 0, and then we need to count out the bonds. So there are 6 bonds to sulfur, so that means there are 12 bonding electrons divided by 2, and sulfur is neutral as well. Okay, so we have the following Lewis structure, and we can also draw a resonance structure for this as well. So I'll draw some examples of what the resonance structures might look like. We might have a double bonded oxygen here and make this single bonded. Like that. And it's basically just experimenting with all the different ways double bonds can be formed for this ion. Okay, so here's an example of 3 different resonance structures. And the last part of the question says if you minimize the formal charge on sulfur, which we did, how many double bonds would you draw on this Lewis structure? So therefore we can draw 2 double bonds to minimize the charge on sulfur. Okay, so let's see what the junior tutor said. Formal charges happen when more or fewer electrons are present in the valence electrons of the atoms in the Lewis structure than the individual atom's valence electrons. An increase in valence electrons would mean that the formal charge becomes more negative, and while a decrease in electrons in the valence shell makes the formal charge to be more positive. For the sulfate ion, the Lewis structure with the least formal charge is, and they found out the total number of valence electrons first, it was 32, and they drew a Lewis structure with 2 double bonded oxygens, which is letter C. Okay, so this solution is correct. Okay, so question number 2. Draw the Lewis dot structure for methane, which is CH4. Predict, according to the Vesper theory, what is the molecular geometry of methane and what are the predicted bond angles? Okay, so first we need to write the Lewis structure for methane. And to do that, we just need to find the total number of valence electrons for this molecule. Carbon has 4 valence electrons, and hydrogen has 1. And since there are 4 hydrogen atoms, we multiply this by 4, and we get a total of 8 valence electrons. Okay, so now let's draw a skeletal structure showing carbon as our central atom since it is able to form multiple bonds, unlike hydrogen, which can only form the one bond since it only has 1 valence electron. Okay, so we can draw 4 single bonds to hydrogen, And if we count out the electrons we've drawn so far, where each bond contains 2 bonding electrons, we already have our 8 electrons needed for the structure. So now, when we analyze it, we can find out the molecular geometry and the predicted bond angles. So looking at the central atom, which is this carbon, we see that it has 0 lone pairs and 4 bonded atoms. So we can use a Vesper theory chart to see the type of shape and the different bond angles, and also a lot of other different identities of the carbon. Okay, so if we see by using this Vesper theory table, when your central atom has 4 bonded atoms and 0 lone pairs, its molecular shape and electron geometry is tetrahedral. I'm just going to write molecular shape and electron geometry is tetrahedral. So since there are no lone pairs on the carbon, the molecular shape and electron geometry would be the same. The carbon is sp3 hybridized. And the expected bond angles are 109.5 degrees. Okay, so the junior tutor said that we first need to calculate number of valence electrons, so they got 8. And I don't think the picture is showing, but it sounds like they got the correct answer. Tetrahedral electron pair geometry. And bond angles equal to 109.5. Okay, so this solution is correct. But I'll just describe what it looks like. Okay, so question number 3. Use the periodic table to write condensed electron configuration for A, cobalt, and Te, which I believe is tellurium. Yep, tellurium. Okay, so cobalt and tellurium. Okay, so when writing out the electron configuration, we first need to divide our periodic table into the different orbitals. Okay, so this is what it would look like. So our first 2 columns plus helium is known as the S block, and this green section here is the P block, and the middle transition metals is the D block, and the last 2 rows are the lactanides and actinides. Okay, so starting from hydrogen, we would move left to right across the periodic table, writing the row number followed by the block letter. And then in the superscripts, we can show how many electrons are in that orbital. So when we write the condensed form of the electron configuration, we would find the noble gas that comes before it. So in cobalt's case, it's argon. And then we would write that in square brackets. And then continue on writing the rest of the electron configuration. Okay, so argon, and then we move down to row 4 and write the block letter S. 2 electrons can fit in an s orbital. And then we count out how many electrons are in the d orbital up to the cobalt. So 1, 2, 3, 4, 5, 6, 7. So we write 3d7. Okay, so let's do the same thing for tellurium. The noble gas that comes before tellurium, which is shown here, atomic number 43, is krypton. And then writing out the remaining electron configuration, we write 5s2. And then you can see here that the F block is kind of inserted in the middle, but we don't have to worry about that since that's in the next row. And we would just continue on. Oh, tellurium's found right here, sorry. 52. So we have a full d orbital, 4d10. And then tellurium is found here, so we write 5p4. Yeah, it's kind of hard to read the letters, but I just found actual tellurium right here. Okay, so we have our 2 shortened electron configurations for these elements. And the junior tutor sums up how one would write a condensed electron configuration. And for cobalt, they got the same answer, argon 4s2 3d7, and tellurium was krypton 5s2 4d10 5p4. Okay, so this solution is correct. Okay, so question number 4 is to predict the product of the following reaction and include hydrogen atoms in your structure. Okay, so let's start off by writing out a proposed mechanism for this reaction. So we have an alkene. So this is a butene. And it reacts with water. So I'm just going to draw water like this so we can easily show the mechanism. And the first step is that the double bond gets reduced to form the following intermediate. Where we now have a single bonded carbon structure. Like so. And notice that one of the carbons is missing a third bond, making it have a neutral charge. But another water molecule can come in oh, I just noticed that this should be a methyl group. Okay, so another water molecule will come in and neutralize that positive charge. And we get the next structure, which now has the water molecule bonded to the carbon. So now the oxygen has a positive charge. But another water molecule can come in and deprotonate this OH, like so, to form our final product, which now has an alcohol group on one of the carbons. Like so. Okay, so now let's see what the junior tutor said. The treatment of alkene with water and sulfuric acid results in an acid-catalyzed hydration wherein the alkene is converted to the alcohol. The reaction typically proceeds via Markovnikov addition, but since the given alkene is symmetrical, a hydroxyl group can attach to either one of the carbons. Scheme 1 shows the mechanism by which the reaction will proceed, while Scheme 2 shows the general reaction involved. Note that in the presence of water, sulfuric acid dissociates to protons to produce hydronium ions. Okay, so they also drew out a mechanism. We have the double bond getting reduced, a water molecule coming in to attack the carbon, and then we have our final product, which is 1-methyl propanol. Okay, so this solution is correct. Okay, so question number 5 asks, what is the IUPAC name for the compound shown below? Okay, so let's draw out these compounds. We have 4 different compounds, and for the first compound, it's just linear hydrocarbons. With like also a side chain going down like this. Okay, so when writing out the name for these compounds, we first need to find out the parent chain. So I'm just going to put a general rules. So we need to identify the parent chain. Which is the longest and contains the most important groups. Okay, so let's count out where the longest chain would be. So if we count out all these carbons, where each of these ends is a carbon, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And if we were to go down and try out the side group, we get 1, 2, 3, 4, 5, 6, 7, 8, 9. So we get 9 either way. So just to make it easier, I'm just going to circle the main horizontal group. Okay, so now let's count out the carbons and find out where our functional group is. So the second step is to number your carbons. And in the end, we want to have the lowest sum of numbers in the name. I'm just going to write have the lowest sum of numbers possible. So for example, if we started counting from here and made this carbon 1, 2, 3, 4, 5, 6, notice that our chain, our side chain would be on carbon 6. But if we started counting from the end, 1, 2, 3, 4, our chain would be on carbon 4 as opposed to 6. So since 4 is the lowest number here, we would name it as carbon 4. Okay, so now we just need to identify the side groups for step 3. Okay, so I'm just going to circle this small chain as the only side group for this structure. And if we number it as well, you'll see that it only contains 3 carbons. So this is known as a propyl group. So now when we name this structure, we first need to write out which carbon contains the propyl group. So it's carbon 4. So we write 4-propyl. And since our parent chain is 9 carbons long, we use the prefix nona or known. And the fact that there are only single bonds in this chain, then the parent would just end in ane. So our final answer is 4-propyl nonane. Okay, so now let's do the same methods and answer part B. So it's a more obscure looking carbon chain. Okay, and again, we want to circle the longest parent chain with the most important groups. So again, it's just carbon and hydrogen, so we basically just need to circle the longest chain. I'm gonna make room to write some numbers in as well. And we get the following for the longest chain. And now I want to number my carbons. So we'll see where our side group is, and it's kind of in the middle here. So if we started counting from the top, you have 1, 2, 3, 4. So it would be carbon 4, but if we started counting from the bottom, 2, 3, 4, it's also carbon 4. So it doesn't really matter where you number, so I'm just going to start numbering from the top. 1, 2, 3, 4, 5, 6, 7. Okay, so we have a 7 carbon long chain. And just to sum up all the prefixes, I'm going to write them on the side here. So when we have 1 carbon, we write the prefix meth. For 2, it's eth. 3 is prop. 4 is bute. 5 is pent. 6 is hex. 7 is hept. 8 is oct or octa. 9 is nona. And 10 is deca. Okay, so I just summed up all the different prefixes. So here you'll notice that for our side group, it's also a 3-membered carbon like our previous compound, but this time it's attached at carbon 2. So this is not just a propyl group, but we call it isopropyl. Okay, so when we try to name this compound, we start off by identifying which carbon the isopropyl group is on, so it's carbon 4. And then we write isopropyl. And we have a 7 carbon long parent chain. So if we refer to our prefixes, I would use the prefix hept. And again, there's only single bonds in this compound, so it ends in ane. So this compound is 4-isopropyl heptane. Okay, so on to the next compound. So if we look at this next compound, it contains an alcohol group. So when we want to find our parent chain, we know it needs to contain this alcohol group. And typically, this alcohol group would be carbon 1, since there is nothing else on this structure. Our alcohol group would be considered the most important functional group in this structure. So now let's try to count out the number of carbons that we could form and the longest chain. So if we started counting this as carbon 1, 2, 3, and if we started counting going up, 1, 2, 3. So we get the same number of carbons. So I'm just going to count going across 1, 2, 3. And I'll just circle our parent chain, which includes the alcohol group on carbon 1. And now if I identify the side groups, it's a 2 carbon long chain. Oh, I just noticed that, wait, 1, 2, 3, 4. Oh, never mind. So, the longest parent chain actually is the one that goes up. I must have miscounted. So then we would change our numbers to 1, 2, 3, 4. So sometimes it takes some trial and error to realize what your parent chain might be, but it's actually this 4 carbon long chain, and our side group is this 1 methyl group. Okay, so since we only have the 1 alcohol on carbon 1, we don't need to specify which carbon this alcohol group is on, since it's already assumed that it's carbon 1. So the way that this IUPAC name is going to end is just butanol. And already the fact that it ends in -ol tells us that there is an alcohol group on carbon 1. So now we just need to write the beginning of this name. On carbon 2, there is a methyl group. So we write 2-methyl and then butanol. Okay, so now let's name our last compound. So we have a cyclic carbon structure that contains both a bromine and an alcohol group. Okay, so when circling our parent chain, it's pretty much the whole cyclic group, and the alcohol would be included as well. And we know that when we have the alcohol, it would be considered carbon 1. And when we want to have the lowest number of numbers possible in the end, I know if I go counterclockwise, then the bromine would be on carbon 2 as opposed to carbon 5. So I'm going to start numbering, going here. So we have a 5 carbon cyclic chain. So we know that the parent group would be pent. And on carbon 2 is our bromine. So we write 2-bromo. And the name of our parent, since it's 5 carbons long and it's in a ring structure, then we use the term cyclo. So we use cyclo, pent, and then it ends in an -ol, so pentanol. Okay, so those are all of the names for these compounds. So let's see what the junior tutor said. In naming alkanes and alcohols, the parent chain corresponds to the longest possible chain of the compound, and the prefix used for the name varies depending on the number of carbon atoms comprising the chain. The table shows some of the prefixes used in naming alkanes. Note that if the compound is an alkane, the prefix is added to -ane, while if it is an alcohol, the prefix is added to -ol, and the parent chain is the one bearing the hydroxyl group. In the case of cyclic compounds, on the other hand, just add cyclo before the parent name. Okay, so they also summed up however many carbons you have will have the parent of like either meth, eth, prop, or bute. And they also said the name of the alkane as well. And then after naming the parent chain, assign locants to the chain in such a way that the substituents get the lowest possible number, and then name them. If it is an alkyl group, the prefixes shown in the table also apply, but instead of -ane, -il is used. Okay, so for part A, in the red, they showed the parent chain, and they also got 4-propyl nonane. For part B, they have the longest chain here, and got the 4-isopropyl heptane. So they said the substituent is composed of 3 carbon atoms, but note that compared to the molecule in part A, the propyl substituent is attached from the second carbon of the alkyl substituent. So this is isopropyl. And for part C, the longest possible chain is composed of 4 carbon atoms, so the name of the parent is butanol. The substituent, on the other hand, is an alkyl group composed of 1 carbon atom, so its name is methyl. Therefore, it's 2-methylbutanol. And lastly, for part D, 5-carbon cyclic structure. So it's cyclopentanol and 2-bromocyclopentanol. Okay, so this solution is correct. Okay, so question number 6. Draw the Lewis structure for methane, which is CH4. According to Vesper theory, what is the molecular geometry of methane, and what are the predicted bond angles? Okay, so when writing out the Lewis structure, we first need to calculate the total number of valence electrons. Carbon has 4 valence electrons, and hydrogen has 1. And since there are 4 hydrogen atoms, we multiply this number by 4 to give us a total of 8 valence electrons. So now, when writing the skeletal structure, I'm going to write carbon as our central atom, and then I'm just going to form 4 bonds with my hydrogens. So the reason why carbon is our central atom as opposed to the hydrogen is because carbon is able to make multiple bonds. Hydrogen is only able to make a single bond because it only has 1 valence electron to participate in the bonding. Okay, so now I have this structure for methane, and if I count out how many electrons I've drawn so far, where each bond contains 2 bonded atoms, then I have my 8 electrons already in the structure, so this would be the correct Lewis structure. So for the second part of the question, according to Vesper theory, what is the molecular geometry of methane, and what are the predicted bond angles? So we need to analyze our central carbon for this structure, and we'll see that the carbon has 0 lone pairs, and it has 4 bonded atoms. So if we use a Vesper theory table, like this one, we can find out a lot of things about it, like its molecular shape and its electron geometry. So when we have 4 bonded atoms and 0 lone pairs, we have a tetrahedral molecular shape and electron geometry. So I'm just going to write molecular shape and electron geometry. Is both tetrahedral. Okay, so since there are no lone pairs on the carbon, we would have the same molecular shape and electron geometry. And the carbon would be sp3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 , 3 And the predicted bond angles are around 109.5 degrees. Okay, so now let's see what the junior tutor said. For us to use the Vesper theory, we need to first write the Lewis structure of the molecule. The molecular geometry of a molecule can be determined depending on the number of bonds present and the number of lone pairs present in the central atom. For molecular geometry has also its predicted bond angles for the molecule. The methane molecule will have carbon as its central atom with the 4 hydrogens bonded to it. Carbon has 4 valence electrons, while each hydrogen has 1, and the valence electron of the hydrogen will be shared with the central atom, which can be represented as a single bond, hence its Lewis structure is the following. So using Vesper, it has tetrahedral molecular geometry with bond angles of 109.5 degrees. Okay, so this solution is correct. Okay, so question number 7 is, what is the formula mass of barium phosphate? Ba3 PO4 2. Okay, so the phosphate ion is an example of a polyatomic ion, and barium is just one of the alkaline metals. And to calculate the molar mass of this compound, we would need all the different molar masses of all of the atoms involved. So I would need the molar mass of barium, phosphate, and oxygen. Oops. I'm going to have to look up the molar masses for barium and phosphate since I don't know them off the top of my head. But for oxygen, it is around 16 grams per mole. Okay, so using a periodic table, let's click on this one. We can find out its atomic mass or molar mass of each of these elements. So this is barium, it's an alkaline earth metal, and its atomic mass, they have it in units of AMU, but this is equivalent to its molar mass, so we can just say 137.33 grams per mole. And now let's find phosphate on the periodic table, or phosphorus, sorry. And its atomic mass is 30.97 grams per mole. Okay, so now that I know all the individual molar masses, I can write out an expression to find out the molar mass of this entire compound. So since we have 3 barium atoms, it's going to be 3 times the molar mass of barium, and in total we have 2 phosphorus atoms, so 2 times the molar mass of phosphorus, and we have 4 oxygens inside the bracket that has a subscript of 2, so in total we have 8 oxygen atoms, so we do 8 times the molar mass of oxygen. Okay, so now we just need to add all the values up. So we found the molar mass of barium to be 137.33 grams per mole. The molar mass of phosphorus was 30.97 grams per mole. And finally, the molar mass of oxygen is around 16 grams per mole. So adding all these values up, we get a total molar mass of 601.93 grams per mole. Okay, so let's see what the junior tutor said. This is option E for our multiple choice. And the junior tutor said that the formula mass of a compound is the sum of the individual atomic masses of the elements comprising the compound. Thus, the formula of barium phosphate is the following, where it's equal to 601.93. Okay, so this solution is correct. Okay, so those are all the questions for this session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, you can give it a thumbs up or a comment, and you can share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.